Everybody, notebook? Landscape mode, not portrait. And coffee, we are a go. And that's the perfect temperature. All right, where's my purple marker? In the middle of your page, we're gonna draw, and we're going to label stuff. Okay, so what?
I
got you.
So here's the thing. You could, I tell you what, probably what makes the most sense is somebody you trust taking these notes, and then you like, and it goes. There's a machine that goes, and it goes, makes a copy. Right? Okay. All right. So here we go. Put a circle with an E in it. Guess what that is?
Earth.
Yeah, we're going to say that's Earth because our heading, by the way, you don't have to write the heading if you don't want to. It's orbits. Orbits, okay? And I'm sorry if this disappoints many of you, too many of you, but I know we've been doing a lot of math lately. You guys are super excited about it, but is it okay if today's lesson doesn't use any numbers?
Yes. Amen.
Is that all right?
Yes.
Okay. So what that does to this physics class for today, intro to physics class for today, is it puts a C word in front of it. It's conceptual now. Because it's not nailed down with math, we're going to call it conceptual physics for today. So orbits, conceptual, what goes around the Earth?
The moon. And the sun.
And a bunch of...
No.
Hold up! He says the moon and sun! No. We left that thinking behind a few centuries ago. Okay, so we got the moon. Put a little M on it like it's an M&M. Peanut or regular?
Peanut.
Or peanut butter.
Peanut butter.
Peanut butter. But here's the thing, though. I can eat peanut M&Ms all day long, but if I eat peanut butter M&Ms, they're actually too rich, and I'll get like, it starts to, it turns like my tummy sour. You know what I mean? Anyway, so the moon does what around the Earth?
Orbits.
Hey, that's beautiful. Okay. Now, but let's think about this for a second. What does the moon, or what would the moon do if it weren't for the Earth? It would run away?
Yeah.
Think it wouldn't be running away because the Earth wouldn't be there. So, Newton's first law of motion. Inertia. So, related to this, somebody tell me, how does it relate to this? The moon is the thing. An object in motion. The moon is in motion.
Stays in motion.
It will stay in motion and it will continue to do the exact type of motion. It will move with the same exact instant velocity forever unless acted upon by, in this case, Earth's what kind of force? So we've got gravity acting on it. That's the force acting on it, okay? If it weren't for that, think back to instantaneous velocity. In any one moment, that means zero time, right? An instant is timeless. It's like, what is it doing right now? It has an instantaneous velocity. If you took that instantaneous velocity and extended it out indefinitely, what would the moon's motion look like? What did you say? Straight. It would be linear. Guys, if not for Earth's gravity, the moon's motion would be linear. I don't like that. It would be linear. In fact, write that down. Linear motion. Newton's first law of motion. If an object is in motion, it's going to do whatever it's doing in that moment continuously, which means Newton's first law of motion is talking about linear motion or no motion at all if it were at rest, right? Okay. But we got gravity. I'm gonna throw another term in there. You got linear motion. If we include the moon's mass, we haven't touched this yet, I don't think. What if you have the moon's velocity times its mass? Does anybody know what that gets us? Little definition here. This is a new definition for you. We're going to cover it soon, I'm sure. It would be linear momentum. Because momentum is equal to velocity times mass. Okay? Now, I know that looks like math, but I'm not putting any numbers to it, so you can't yell at me. Okay? It's just a relationship thing. We understand. Okay? Now, and if I don't move long enough, let me know so I move so you can see what the board says. So that's Newton's first law as it relates to the arrangement we've got here. What about the third? For every
force, there is an equal and opposite reaction.
force. So between the Earth and the Moon, the action force is you already pointed it out, the gravitational force of the Earth pulling on the Moon. But for every force or action force, there's an equal and opposite reaction force. Where's that force coming from? The Moon, acting upon the Earth. So the Earth pulls the Moon pulls right back with an equal and opposite force.
Is that how they say balance?
Huh?
Is that how they say balance?
Oh, hold on. Hold on. The question is, a very good question. He says, is that how they stay in balance? Not quite.
Isn't that tides?
Good. Thank you. Good. The gravity from the Moon upon the Earth creates the tides, right? And then they're more strong if the Moon is in line with the Sun, because then they're both pulling on the Earth, right? And the water. All right. Good. Okay, you're already ahead of me now. Okay, so we've got Newton's third law here. Pull, equal and opposite pull. The balance. Who used the word balance? Good job. So where can I write this? I'm going to write this over here. There is a balance. You can write it wherever you have room, okay? There is a balance between what? We've got two things we've discussed here. We got that and this. We have the force of gravity in balance, or, spoiler alert, near balance with the Moon's momentum, okay? The Moon's linear momentum. So gravity holding on to the Moon, holding the Moon and the Earth system together, balanced with the linear momentum of the Moon, which I'm just going to call it momentum. And the M has an extra line there. There we go. All right, now I'm going to draw some more on here. Wait, I said some more on here, and it sounded like I said there's some more on here. More. I try not to be. Okay, there is an angle here, right? Between, by the way, this is called linear motion. We could call this, it would be a linear path, right? If not for the Earth's gravitational force, we'd have a linear path that the Moon would be on. And then we also have the actual orbital path, because the Earth's gravity means that the Moon is constantly doing what?
Rotating. Around its axis. Orbiting.
Around the Earth, pulling.
Orbiting around the Earth.
If I have this marker,
Falling.
and yes, and I throw it, it'd be moving like the Moon with linear path, but that linear path would be curved down because it would be falling. But does the Moon actually come down? No. The Moon is constantly falling, but never drops because of the balance between gravity and momentum. Does that check out? Okay, good. What else? What else? What else? We also have an angle here between the orbital path and the line connecting the moon and the earth by the gravity, and that's perpendicular, right, to the linear path. Now, are orbits perfect circles? Almost never. Are there instances where you might temporarily have an orbit maybe one time around be like ridiculously close to a perfect circle? Probably. But more often than not, orbits are elliptical. Okay? So you could say with orbits over here, hey, orbits are ellipses. They are elliptical. They're not perfectly circular. So depending on where the moon is around the Earth, it may or may not be exactly 90 degrees, that angle between the line of gravity and the linear path. But on average, does that make sense? On average, this would be a right angle. Make sense? Sometimes it would be a little bit, what would this be, obtuse? More than a 90? Or acute, less than a 90, is that right? Am I using the terms right? Okay. But on average, it'd be a 90. This angle right here, 90 degrees, has a lot to do with another term called angular momentum. And again, we're not using any numbers to describe, so I've got to do my best to reach back into my memory. In your way. I just need to do this. Just disappear for a second so y'all can catch. You guys need to catch up. Next thing, the moon has momentum. We've said that already, and that momentum is curved by the Earth's gravity. We have an angle here. Depending on where the moon is, though, closer or further away, it would have more or less speed. Let me see if I can relate that to something. If that doesn't make sense, how many of you guys have ever seen figure skating? Okay, most of you, good. So if the skater is doing one of the really fast spin things and they got their hands in tight and they're spinning, don't they spin like really fast? And then if they put their arms out, they start slowing down. If they put their arms all the way out, they slow down the most, right? It's the same thing. That is an example of angular momentum. So they're preserving the momentum, but depending on how close in they bring in the mass, the tighter the mass in, the higher the speed has to go to keep balance. And then as it goes out, as the arms go out, or in this case as the moon goes out further, has to slow down. Otherwise, you'd be violating laws of physics. The math wouldn't work anymore. You'd have to be getting rid of momentum. Okay, hold on. Let's think about this for a second. Could the moon or the Earth magically lose momentum? No, there's stuff that can cause that to happen. So I want you to think. Somebody said tides. Who said tides? Thank you. The moon's mass, gravity, is pulling on the Earth, raising the water levels, making the Earth basically bulge toward the moon, because the water it's a fluid, right? It can get pulled toward it, okay? What kind of friction do you think might be involved with the tides? Do you remember our 4 types of friction? Fluid friction, good. So we had static, sliding, rolling, and fluid. If we're talking about water on Earth bulging to one side, it's going to be interacting with the seafloor, it's going to be interacting with the shorelines, it's going to be interacting with a whole bunch of stuff, right? So the gravity from the moon, those tides that it's creating, it's actually creating drag on the Earth. And what it's called is gravitational friction. Write that down. Gravitational Friction. Okay, let me try to explain. I think I have already, but I want to wrap that up in a nice, neat package and put a bow on it. Think about that water abrading all of the surfaces it comes in contact with, to include itself. So the ocean currents above and below, they pass by each other too, right? The water molecules. All of that friction does what, do you think, to the Earth's actual rotation on its axis? It slows it down. The moon, through the tides, is slowing the Earth's spin down. If you slow the Earth's spin down, and these two bodies are gravitationally held together, if you slow the figure skater down, what happens to their arms?
They go out.
They go out. Okay? If the energy is preserved, if the momentum is preserved, then the arms would go, they'd have to go out. The moon, as it's slowing the Earth spin down, it has to move out.
Whoa.
The moon is moving away from the Earth. The moon is ejecting itself out from the Earth because of its gravitational influence upon it by about 1.5 inches a year. 1.5 inches per year, the moon is moving away, on average. On average. How do they know that? Well, they put this mirror thing up on the moon when they went there, and they can bounce laser beams off of it and calculate the distance.
Whoa.
So, on average, 1.5 inches a year further out. We don't have to really worry about this because human lifetimes are short. Human civilization has been incredibly short compared to, celestial objects and orbital mechanics and things like that. Okay? But it's moving away. As it moves away, we're going to get this feedback loop. Because as it moves away, gravitational influence is reduced. The further an object is away from another object, we're going to see this with math the next lesson. I promise we'll get to the math. I know you were disappointed today. But as you move objects away from each other, their gravitational attraction is reduced. So the moon gravitationally is causing friction on the Earth to slow it down, which means the moon has to move away, and then the gravitational effect will be less. So there's still got linear momentum. Moon wants to get away, but there's less gravitational attraction, so even more quickly the moon will move away, right? All right, let's rewind the clock. If the moon's moving away, that means in the past the moon must have been closer. Could you imagine looking up in the night sky and seeing a larger moon?
That'd be cool.
What effect would that have on the planet? The tides would be way bigger because the moon's closer, so gravity is more powerful. Okay?
Whoa.
There's a lot going on here, right? This one image, there's a lot going on here to talk about and explain. I'm going to take a step back, make sure I've got everything. Right away, I see one that I didn't put up here. Yes, absolutely. Take a pass. Tidal lock. Tidal lock. And I'm going to explain it as best I can. You guys put it in your notes, with whatever wording you want. I'm going to put my marker down. Yes.
Does it say L-A-K or L-O-C-K?
L-O-C-K. I'm sorry. My handwriting. Sometimes I get my letters too close. L-O-C-K. Is that better? I was supposed to have my marker down. Good grief. Making me pick up my marker. Okay. This is not a model of the moon. It's a model of the Earth. I get it. But I'm going to be the Earth. And this is going to be the moon. Tidal lock. What does that mean? Does anybody know? Yes.
Maybe the tide stays.
Okay, you're thinking about tides like water. I'm thinking tides. Whenever you hear the word tides in physics or astronomy, Tidal just means to do with gravity. Something to do with gravity. So when you hear tidal waves, a tidal wave or the tides, when you're concerned with the oceans, it's caused by gravity. Okay? So when you hear tidal forces, we're talking about gravitational forces, okay? The moon, if I'm the Earth, let's say I'm looking at the Pacific Ocean, okay? Obviously the moon doesn't have Pacific Ocean. I'm just saying it, one part of the moon. As it moves around the Earth's spinning too on its axis, but the moon has always got the same face pointed at the Earth. Has anybody ever noticed that? If you look up at the moon, doesn't matter what day, doesn't matter what time of day, night, whatever, you never get to see like new features.
So there really is a dark side to the moon.
Not a dark side, because as the Earth is traveling around the sun and the moon is going around the Earth, the same face is toward the Earth, but the same face isn't toward the sun.
Oh.
So all sides of the moon get sun, unless you're in a deep crater, right, with shadows over you all the time. But as far as the Earth goes, it's a far side of the moon all the time. It's always the furthest side. So we only get to see. So that's what it means when I say tidal lock. I mean you have one body orbiting another, and their faces are locked. They don't get to see the other side of the one they're locked to. It is actually possible for two celestial bodies, two large objects, to both be tidally locked to each other. So to demonstrate that, you could think about a tether, like a string or a rope, tying two objects together as gravity, and you could throw them, like end over end, tumbling, and they'd be rotating around a center of mass, and they'd both be facing each other the whole time. Does that make sense? That'd be an example of tidally locked, or a model of. Pure tutor, is it Mercury that's almost perfectly tidally locked to the sun, I think? So the day is almost the same length as the year. So imagine if the day was almost the same length as the year, how would the weather be affected? Like the temperatures. So the side that is light for half of the year is going to get ridiculously toasty. The side that's in the dark for half of the year, and then slowly the other side starts to face, right? But it's ridiculously slow. One of the planets was it Proxima Centauri b, the sun. One of its the B is one of the planets, and they believe it's tidally locked to it. That's our nearest celestial neighbor. Anyway, you can look it up if you want. I think that's it. I think that's all I have, new stuff. I did tell you that our lesson yesterday was a 2-dayer, and so I'm still going to give you the rest of the class now. I think I took half. You get the other half of the class to finish up, tidy up. I'll be scrubbing the grades